Dear Diploma CET aspirants, today we'll start with one more important topic, process synchronization and deadlock concept. In a previous video, we have seen the concept related to process and process scheduling, as well as we have also seen inter-process communication. If any process wants to execute, it has to share its data to other process. Then it means that those processes are called cooperative processes. When any one process try to access or share the information or data, its data to other process, then those process should be mutually agreed processes, and those processes share their data to other process. When two or more processes try to access the same data from other process, then there is a chance of data inconsistency. There is a chance of data inconsistency when one process has modified the data and other process has accessed the modified data. Actually, it wanted to use the original data. Such situation leads to data inconsistency. This data inconsistency can be synchronized with the help of some tools, some algorithms in your operating system. That concept we are saying in operating system as process synchronization. The concept of process synchronization begins with a race condition. That race condition is a situation where several processes access and manipulate the same data concurrently, and the outcome of execution depends on the particular order in which the access take place, is called a race condition. In any operating system, there can be a number of processes. Each process can try to access particular data and try to manipulate that data concurrently. It means that simultaneously multiple processes can access the same data and they are try to modify such data. In this scenario, the sequence or particular order in which the access take place is called race condition. It means that every process is trying to access the particular data to access and modify it. That situation we call it as a race condition. Next is critical section problem. Consider a situation of system consisting of n processes P0, P1, P2, P3 up to Pn minus 1. Each process has a segment of code called critical section in which the process may be changing common variables, updating tables, writing files, and so on. Assume that there are n processes, each processes having their own code, execution code. That code we call it as a segment of a code or small piece of code. In that code we call it as a critical section. That critical section, that important code is going to perform some operations like changing the value of variable or changing the table content or modifying the file content. That code is going to do the following operations. The important features of the system is that when one process is executing its critical section, no other process is to be allowed to execute in its critical section. Assume that every process is executing in its critical section. It means that every process is trying to access a particular file and modifying it. Then It leads to what? It leads to data inconsistency. To make the process synchronization or cooperative process execute in some order, what I need to do is I need to execute a processes in some order. It means that if one process is executing in its critical section, other processes should not enter into its critical section. It means that every one process at a time try to execute in its critical section. The critical section problem is to design a protocol that that the process can use that a process can to use to cooperate. Each process must request permission to enter its critical section. This is very important. Suppose if any process try to execute some important code, that process has to take the permission from operating system. If operating system has given permission, then that process is allowed to enter its critical section. In that case, some other processes will not be allowed to enter into the critical section. The section of each process must request the permission to enter its critical section. The section of code implementing this request is called entry section. Then the critical section may be followed by an exit section. The remaining code is the remainder section. For any process, if it wants to enter into its critical section is nothing but it is the important segment of code it wants to execute. So any process try to enter into its critical section, it has to follow critical section has three sections: entry section, exit section, and remainder section. If it wants to enter into the critical section, it has to take the permission from the operating system. That section we call it as a entry section. Then once it takes the permission from the operating system, it has the exit section. Whatever the code it wants to execute, segment of code, that is what our remainder section. This a solution to this critical section problem must satisfy the three basic requirement. Those are called mutual exclusion, progress, bounded waiting. Mutual exclusion means if process pi is executing in its critical section, it means that ith process is executing in its critical section, then no other process can be executing in their critical section. It means that only one process is allowed to execute in its critical section permitted by the operating system. Other processes will not be allowed to execute in their critical section. This we call it as a mutual exclusion. This requirement should be satisfied. Second requirement is progress. Progress is nothing but if no process is executing in its critical section and some process wish to enter their critical section, then only those processes that are not executing in their remainder section can participate in deciding which will be enter its critical section next. This selection cannot be postponed indefinitely. It means that suppose no processes are executing in their critical section, but they are some are maybe executing in its remainder section. If any process wants to enter into its critical section, then only those processes are allowed which wants to enter into the critical section. It means that some process wish to enter their critical section, then only those processes that are not executing in their remainder section will be allowed or can participate in deciding which will be entered in its critical section. And while selecting these processes for entering into the critical section will not go into indefinite. Those selections should be made very soon. The third requirement is bounded waiting. There exists a bound or a limit on the number of times that other processes are allowed to enter their critical section. It means that every process has a limit of entering into the its critical section, and if they enter more number of times, the operating system should not allow such processes for entering into the critical section. After a process has made a request to enter its critical section and before that request is granted, these are the three requirements it has to meet to overcome the problem of critical section. First one is mutual exclusion, progress, then bounded waiting. Next important concept or tool for process synchronization is semaphores. Semaphores, the hardware based solution to the critical section problem. To overcome this difficulty, we can use the synchronization tool called semaphore. Semaphore are the solution for critical section problem. This is hardware based solution to overcome the critical section problem. Here in examination, he asked the question related to definition of critical section and what are the three requirements for solving the critical section problem. Those are mutual exclusion, progress, and bounded waiting. He may ask the definition of race condition, and in semaphores he give the symbol S. What is S indicates, what is V indicates, what is P indicates, that you need to mention in your exam. A semaphore S is an integer variable. It is an integer variable. Apart from initialization, is accessed only through two standard atomic operations. This S can be accessed only to atomic operation. One is called wait, another is signal. These two operations or functions are used to perform the semaphore operation. Usually the S should be an integer value. What is the meaning of wait and signal here is, the wait operation was originally termed P. For simple question, he asks in operating system or synchronization what P indicates or what V indicates. Here two operations we have for semaphore is wait and signal. Wait was originally termed as P and signal was originally termed as V. Here P stands for test in your Dutch. P stands for test, to test in your Dutch language, and V stands for to increment in your Dutch language. Here Dutch meaning P stands for proberen. Proberen in Dutch is nothing but to test. V here is vergon, that it means that increment. In Dutch, vergon is nothing but to increment. You just remember P and V. P is nothing but wait, V is nothing but signal. Why I use P? To test the parameter. Why I use the V to increment the value. Here for wait operation, I have the code wait of S. S is nothing but it is an semaphore. It has an integer value. File S should be lesser than or equal to 0. It means that if I have a value, S value lesser than 0 or equal to 0, then I should not do any operation, should not perform any operation. If S value is greater than 0, then I have to do some operation. Yes, you know that S is an integer value. If its value is less or equal to 0, I am not performing any operation on it. Next, if I use the signal when my S value is greater than 0, then I can go with the signal. In S, in signal I am passing the S value. I know that S value is an integer. When I call the signal function, it's going to increment the value value of S. What is S? Suppose I have the S value as 5. 5 is what? 5 is an semaphore here. It is an integer value. When I test it for weight, when I test it for weight, S is lesser than or equal to 0. S is nothing but 5. 5 should not be lesser than 0. So that time I am not performing any operation, then I am moving to the next operation, that is signal. Here you know that S is 5, I am incrementing value for that test. You know that signal is for incrementing and weight is for test operation. Signal is denoted by V and test is denoted by P. The value of counting semaphore can range over an unrestricted domain. We have some other type of semaphore, those are called counting semaphore. Those counting semaphore can go with unrestricted domain, like we can use this counting semaphore for different purposes. For binary semaphore, we can have the range only from 0 to 1. Binary semaphores are also known as mutex locks. Mutex are nothing but mutual exclusive locks. Next important concept is a deadlock. A deadlock, before starting with our deadlock concept, we should know the what is the concept behind deadlock. In book he has given the uh, example of train. If two train try to cross the bridge, particular bridge, then any one bridge any one train has to wait some other side, then only the other train should pass through that particular bridge. If these two train try to pass through a bridge at same time, there is a accident. So it means that if multiple processes are trying to access the same resource, then there is a chance of deadlock. Deadlock is nothing but it is the situation where multiple processes are trying to access the same resources. That time that resource is not available, that leads to what? Deadlock situation. Deadlock is nothing but indefinite of blocking of execution. The system will be blocked for indefinitely because of there is a lack of resources required for the processes. For any system, we have the deadlock system model. For any process, the process wants to use the some resources. First, resources in computer systems are nothing but those are the memories, those are the clock cycles, those are the files. Those are all called the resources in your computer system. For any process, if it wants to use the resources, it has to perform three basic operations. Before using any resource, the process has to request for that process. If it is idle, free, then that resource will be allocated for that process. The next, if it is not free, that particular process has to wait for that process until the other process has released that resource. The second operation is use. If the resource is free, then the operating system will allocate that resource for that process. Then the process uses the resources. Then after using, it has to use it. Then the last operation is release. Once the process has used that resource, it has to release for other processes. Now, how do I say that there is a deadlock in my system? for any operating system, I should that system should satisfy some conditions. Those are called necessary conditions. If it has satisfied any one of the condition, then I say that the system is in deadlock state. First condition is any one question will come from this deadlock condition, necessary condition. First condition is mutual exclusion. That mutual exclusion says at least one resource must be in a non-shareable mode, that is only one process at a time can use the resource. Assume that I have only one resource. If n number of processes try to access that resource, if that resource is non-shareable means that resources cannot be shared among n number of processes at same time. Such we call it as a non-shareable resource. In that condition, if more number of processes are trying to access the non-shareable resource, then that leads to what? It leads to mutual exclusion condition. If it is satisfied, then there is a chance of deadlock. The second is hold and wait. Suppose the process P1 is holding some resource R1, then that same P1 process is requesting another resource R2 that is held by some other process. That leads to what? Deadlock. It has satisfied the second condition, hold and wait. A process must be holding at least one resource and waiting to acquire additional resources that are currently being held by other process. As I said, P1 is requesting R1 resources and that R1 resource is held by some other process. This leads to condition what? Hold and wait. It is holding one resource and requesting for another resource. The third condition is necessary condition is preemption. No preemption. No preemption means resources cannot be preempted. That is, a resource can be released only voluntarily by the process holding it after that process has completed a task. It means that preemption means when any process requested for any resource, that resource has to be released by the process. That we call it as a preemption. If any process try to access the particular resource, that resource is held by some other process. If that process does not release that particular resource, it means that no preemption. It has not preempted that resources requested by some other process. That condition we call it as a no preemption. No preemption, if it is satisfied, it leads to a deadlock. One more condition, necessary condition is circular wait. Circular wait, we have the set of processes P1, P0, P1 up to Pn. For waiting for some resources, waiting process must exist in such a way that P0 is waiting for R1, R1 is held by P2, P2 is requesting R2, R2 is held by P3. Again, such P3 is held by R3 is held by again P0. This circular we call it as a circular wait. Until any process releases the resource, the other processes will not get the resources requested for it. This will be in circular fashion. This leads to what? It leads to deadlock. These are the four necessary conditions in for having the deadlock in our system. If any one condition satisfied, our system goes into the deadlock state. First, I need to understand what is a resource allocation graph. Some question may come from resource allocation graph. In this diagram, you need to understand the representation of this diagram. The circle represents the process, a rectangle represents the resources. Within the rectangle, we have the dots. Dot is nothing but instance of particular resource. Assume that we have the printer. Printer is a resource. Suppose I have two printers, it means that I have two instances of same resource. Here if I have two printer, that particular rectangle I am writing two dots, it means that that particular resource has three instances of same resource. Suppose I have five printers, printer is a resource, but how many numbers I have five numbers. So within that particular resource I have five dots are represents the instance of particular resource. Here in first resource R1 we have only one instance, it means that only one resource is there, and in R2 we have two instances, in R3 we have only one instances, in R4 I have three instances. Hope you understood the meaning of instance. As I said, processes are represented by circle and resources are represented by rectangle. Within the rectangle, dots represents the instance of particular resource. We have two types of edges here. Edges, assignment edge and request edge. These are very important in your resource allocation graph. Resource allocation graph, a deadlock can be described more precisely in terms of directed graph, that is resource allocation graph. I can represent my deadlock through the help of resource allocation graph. Resource allocation graph are also called RAG. This graph consists of set of vertices V and set of edges E. The set of vertices V is partitioned into two different types of nodes, P equal to P1 comma P2 up to Pn, and the set consisting of active process in the system R1, R2 up to Rm. A directed edge is from process Pi to resource type Rj is denoted by Pi to Rj. It means that Pi ith process is requesting jth resource. For this diagram, resource allocation graph, as I said, we have two edges, request edge and assignment edge. What is the meaning of request edge and assignment edges? You may ask the question on this also. If process is requesting any particular resource, that leads to what? Request edge. Request edge always from process to resource, edge from process towards the resource. But assignment edge, it is reverse. The assignment edge will be from resource to process. From resource to process. I repeat, request edge will be always from process to resource. Assignment edge will be always from resource to process. What is the meaning of this request edge is any process can request any number of resource. It has the edge, direction edge. Assignment edge is nothing but it is from a resource to process. It indicates that that particular process, that particular resource has assigned to particular process. That particular resource has assigned to particular process. That is nothing but assignment edge. That we represented by Rj to Pi. It means that ith process, jth resource has assigned to ith process. Usually this resource allocation graph is used for identifying the deadlock in a system. This resource allocation is used for single instances deadlock detection algorithm. We will be seeing this in detail. Next, for handling deadlock, what are the different methods I use for handling the deadlock? There are three basic methods I follow for handling the deadlock. First, what I do, we can use a protocol to prevent or avoid a deadlock, ensuring that the system will never enter a deadlock state. What I do, I use the protocol. I can prevent the deadlock or I can avoid the deadlock. The second is we can allow the system to enter a deadlock state, detect it and recover it. Let the system goes into the deadlock state, then after going into the deadlock state I just detect the deadlock, then the system is in deadlock state, I just recover from the deadlock. The third method is, even though there is a deadlock, what I do, I just ignore the data, I just pretend that there is no deadlock in my system. This is the third method. Normally in our real life also we have such of example for three methods I will give. What I do, if there is a raining, then I never go into the raining, because I know that if I go into the rain, there is a chance of I'll get fever and cold. That is what prevention avoiding. Now in second method what I do, I'll go into the rain and definitely I'll get the fever and cold. What I do, I go to the doctor and get recover from it. Second method. Third method is, after going into the rain, after getting the fever and cold, what I do, I simply pretend that nothing has happened to me. I just pretend that nothing happened to me after getting fever and cold also. These are the three methods we use for handling the deadlock. For deadlock prevention, we use the same concept for this one. For mutual exclusion, we follow the some method for deadlock prevention. Mutual exclusion, what we do, we know that mutual exclusion is nothing but if there is a non shareable resource, then there is a chance of deadlock. If there is a non shareable resource, if I make it as a shareable, then it means that I have prevented, I have avoided the deadlock. It means that with the help of mutual exclusion, I have prevented the deadlock by making non shareable resource as the shareable resource. Next, hold and wait. How do I prevent the deadlock with the help of hold and wait? If hold and wait condition is satisfied, it means that there is a deadlock. What is the meaning of hold and wait? Hold and wait is nothing but if process P1 is trying to access the resource R1 which is held by some P2 process, again that P1 is requesting additional resource, uh, sorry, if P1 is trying to access the R1 resource, R1 is held by some P2 process, but P1 is holding one more process R2. It has the R2 resource, but additionally it is requesting R1 resource. If it is so, it satisfies the condition called hold and wait. To overcome this deadlock condition, what we need to do, we need to prevent it. How do I do? Instead of requesting additional resources, whatever the resources I have with me, I first release them. If I want new resources, then request the new resources. That is done with the help of hold and wait prevention technique. The third one is no preemption. No preemption, if any process requested for resources, if the process which is holding that particular resource, if it is not released, then that leads to what? No preemption condition. Our system has to be designed such that if any process has requested a particular resource, then that resource is held by some other process. That process has to immediately release the resources when the request is made by some other processes. The fourth one is circular wait. I need to break the chain here. If any process try to access the resource, it has to release the previous resources which is held by itself. These are the four deadlock prevention technique. Next we have the deadlock avoidance. Deadlock avoidance, for deadlock avoidance we use Banker's algorithm. before that banker's algorithm, there is the problematic concept behind the banker's algorithm, but concept behind that banker's algorithm is that if any process try to access the resource, it has the capability, then only that resources will be allocated for that process. If the resources are not available, those resources will not be allocated for the process. Assume that name come from this deadlock avoidance algorithm, that is banker's algorithm, is that if anybody wants to take loan from the bank should have the money in it. If bank itself does not have the money, then that bank will not give the loan to the customer. It means that bank first it has the money, then only that will provide the loan for the customer. Same concept we are using in your deadlock avoidance. If the system has the plenty of resources, then only those resources will be allocated for the processes. Until it does not have the resources, those resources will not be allocated for the processes. That is the concept behind your banker's algorithm. Here safe state, unsafe state, we have the concept. If any system, a safe state is the state is safe if the system can allocate resource to each process in some order and still avoid deadlock. Such condition we call it as a safe state. In some order, if I allocate the resources for the process, if it does not achieve those 4 conditions, then that state we call it as a safe state. In sequence, whatever the sequence order, in which order if I allocate the resources for the processes, that sequence I call it as a safe sequence. Then we have a deadlock detection. Deadlock detection for single instance, deadlock detection for multiple instances. For detection, once this is second method, once the deadlock is occurred, I need to detect it and finally I have to recover it. How do I detect the deadlock within the system? For single instances, I can use the resource allocation graph. For multiple instances, I can use the deadlock detection algorithm, that is your banker's algorithm, banker's deadlock detection algorithm. Here in this concept deadlock detection, as earlier I said, a resource allocation graph. The resource allocation graph has the number of resources and number of processes. For single instances, we use this single instance, means each resource has only single instance. For that, I did in this diagram I have not mentioned the single dot in the rectangle. It means that each resource has a single instance. If all resources have only single instance, then we can define a deadlock detection algorithm that uses the variant of resource allocation called wait for graph. We use the for single instance resource allocation, single instance deadlock detection, we use the wait for graph. Wait for graph is nothing but it is the extension version of resource allocation graph. Instead of having the resources in a graph, we are just collapsing the edges from process to resource. Just we are removing, we are converting resource allocation graph to wait for graph just by removing the edges from process to resource and resource to process. It means that we are just collapsing the resource allocation graph into wait for graph. After that, here in this example, I have the edge from P1 to R1. From R1 to I have P2. P1 to R1 I call it as a request edge, R1 to P2 I call it as a assignment edge. What I do, I collapse, I remove the R1 resource, I directly make the edge from P1 to P2. It is there in your wait for graph. Same with the P2 to P3, I have edge from P2 to P4, P2 to R4 and R4 to P3. I remove the R4 resource, then I have the direct edge from P2 to P3 that I have in my diagram in wait for graph. I have one more edge from P2 to P5 through the R3 resource. P2 to R3, that is your request edge, and R3 to P5 it is assignment edge. What I do, I remove the R3 resource, directly I have the edge from P2 to P5 that I reflected in wait for graph in your second B diagram. Whatever the corresponding diagram for this resource allocation graph I will get now, that is your wait for graph. In this, just I am collapsing the resource allocation graph just by removing the resources from the diagram. That diagram we call it as a wait for graph. How do I identify there is a deadlock or not? If I have cycle within a diagram, then if I have a cycle within a diagram, then it means that there is a deadlock. If I don't have the cycle within the graph, then I call it as a there is no deadlock. Here in this case, P1 from P1, P2, P3, P4, again back to P1, there is a cycle. It means that this system has the deadlock. If I want to remove this cycle, then I can change the sequence of edges, sequence edges. How do I do the several instances of a same resource type? With the help of deadlock detection algorithm, that is your Banker's algorithm. The detailed explanation is there with the help of example that won't come for your CET. Only we need to understand the basic concept behind your deadlock. The last concept of your deadlock is recovery from the deadlock. This for deadlock we have used two methods. One is for single instances, one is for multiple instances. For single instances we have used the resource allocation graph. That resource allocation graph you have collapsed or translated into wait for graph. If you have the cycle for that particular graph, it means that there is a deadlock. If there is no cycle, then there is no deadlock. For multiple instances of type resource type, your resource allocation graph does not give the deadlock detection method. For we need to go for again Banker's algorithm. That Banker's detection algorithm will provide the detect the several instances of resource type. The last method is recovery from deadlock. Once I find that there is a deadlock in my system, once I detect it, then how do I recover it? How do I remove the deadlock from my system? I use two basic methods. One is process termination and one more is resource preemption. In process termination, what I do, suppose the deadlock has occurred. Because that deadlock has occurred, that can be seen with the help of Banker's algorithm in detection algorithm. Because of the deadlock has occurred by so many processes, that is done by the deadlock detection algorithm. Here in process termination, how do I terminate the processes which cause the deadlock? What I do, about all the deadlocked processes, suppose there are 5 processes are there in a system. Because of first 2 processes deadlock has occurred, what I do, I abort means terminate those first two processes completely. After terminating, automatically the system becomes normal, then the execution will continue. This is first method. First method says that aborting all the processes which cause the deadlock. The second one is, instead of terminating all the process, what I do, I am terminating one process at same time. I terminate one process, again I am checking whether the deadlock is there, then I terminate next process. If there is no deadlock, I stop the terminating the process. uh, Process termination. In second method, I am terminating the one process at one time. The second method is resource preemption. What I do in first part, we have terminate the process. In second part, what I do, I use the resource preemption. Resource preemption is nothing but the resources allocated for the processes I am going to preempt. I am taking back those resources for the from the processes. We have three concept under this one. Selecting a victim. Selecting a victim means which resource and which process are to be preempted. Suppose I have 10 processes and 10 resources. When there is a deadlock, among 10, which process you are going to select and which resource you are going to select for termination or preemption. That is very important. Selecting a victim. That is also as in the process termination, we must determine the order of preemption and minimize the cost. In which order, if I go terminating the process or preempt the resource, and which process or which resource take the minimal cost, minimal effort, that resource I am going to preempt first. Second is rollback. If you preempt a resource from a process, what should be done with that process? It cannot continue with its normal execution. It is missing some needed resource. We must roll back the process to some safe state and restart it from the that state. It means that suppose I have preempted resources. That resource of that process already executed half. If I preempt, what happens again? It has to start from the beginning. It is not the procedure where it has stopped. It has to begin from that point. So what I do, when I preempt a particular process, it has to roll back from where it has stopped the execution. The third one is starvation. The starvation is nothing but the starvation concept we are also used in our priority scheduling algorithm. How do you ensure that starvation will not occur? That is, how can we guarantee that resource will not always be preempted from the same process? Suppose I have 10 resources and 10 processes. 10th process has 10th resource. Every time when I choose the same resource for preemption, how do we guarantee that you are not choosing the other resources for preemption? Sometime what happens that you are selecting, every time you are selecting the same resources for the preemption. That leads to what? Starvation. It means that you need to select a resources for preemption such that it should not from the same process. Thank you.